We have all seen large language models write flawless code or draft complex essays in a matter of seconds. But ask a machine to cut you a slice of birthday cake in the real world, and you might get a disaster. For all their processing power, today's most advanced AI models are trapped. They live inside server farms, interacting with the world solely through pixels on a 2D screen, lines of code, and digital text. But the tech industry's biggest players are now redirecting billions of dollars in capital away from simple chatbots. Companies led by figures like NVIDIA's Jensen Huang are heavily investing in a new frontier known as physical AI. Physical AI takes the advanced reasoning of multimodal foundation models and embeds it directly into robotic hardware. These machines are designed to understand and navigate the complex three-dimensional spaces we actually live in. Instead of scraping text from the internet, these systems use cameras, LiDAR, and tactile sensors to perceive depth, feel the weight of an object, and map their surroundings in real time. This is a transition from AI as a digital assistant to AI as a mechanical partner. The intelligence is moving from specialized software into machines that can operate within the same physical variables we do. In the digital realm, variables are controlled and predictable. The physical world is chaotic, filled with unpredictable friction, changing lighting, and sudden obstacles. This chart shows the cost curve of training robots. Attempting physical trial and error in the real world is exponentially more expensive and time-consuming than running virtual simulations. Roboticists call this the sim-to-real gap, the massive drop in performance when moving from a perfect simulation to reality. To close this gap, engineers are building world foundation models. These algorithms digest internet-scale video to learn the basic laws of physics, such as gravity, physical momentum, and the concept of object permanence. Next, AI agents enter simulated robot gyms. Here, virtual robots perform physical tasks, like standing up or grabbing a box, millions of times at vastly accelerated speeds. Every time the virtual robot falls or drops an item, it generates synthetic data. This massive feedback loop allows the agent to develop a kind of physical common sense without risking any actual hardware. By mastering the virtual physics engine first, these AI agents arrive in the physical world already equipped to survive, adapt, and handle unpredictable variables. Giving a robot a highly trained brain presents an immediate physical problem. Traditional AI models require massive, energy-draining server farms, which obviously cannot fit inside a mobile robotic body. Researchers are solving this with an entirely different architecture called liquid networks. These are highly efficient neural networks designed to run locally on small computers, directly on the machine, what the industry calls edge compute. The inspiration for this technology comes from a tiny worm known as C. elegans. Biologists have mapped how this organism manages complex navigation using only 302 neurons. By mimicking this biological structure, liquid networks achieve sophisticated decision-making with a fraction of the computational power. Because they are so compact, these networks do something traditional AI cannot. They continue to adapt and learn after their initial training, instantly adjusting to new inputs in their physical environment. Robots equipped with this technology process their surroundings instantly. They react to humans and chaotic environments on the spot, without waiting for data to travel to the cloud and back. In logistics, manufacturing, and autonomous vehicle sectors, machines are already operating on the floor. In modern warehouses, autonomous robots weave through human traffic, handling inventory without a fixed track. Early data shows physical AI can automate 50% more tasks than traditional pre-programmed robots. When they drop an item or encounter an obstacle, they don't freeze. They evaluate the problem and correct their mistake. If a chatbot hallucinates, you get a flawed text document. If a physical AI hallucinates, a heavy machine moving at high speeds acts unpredictably in a human space. This introduces the massive engineering challenge of functional safety. Regulators and developers have to guarantee that agents operating at superhuman speeds will consistently align with strict safety parameters when working alongside people. The economic impact stems from pairing large-scale AI reasoning with tireless mechanical execution. This changes the cost and speed of tasks that once relied on routine physical labor. The integration of these models into hardware means the digital and physical worlds are no longer separate domains for AI. We are left to decide how we will share our physical space with autonomous agents.